Good morning, everybody. That day you've all been waiting for has arrived. So, before I throw it open to questions, what was EE10 all about? All right. Now, sure, in the syllabus, I have all the learning objectives, right? But maybe let's just kind of go somewhat question by question, right? So, if I give you a plot, right? Um, what is it? Right? Ramps, steps, things like that. And just the ability to recognize a shape and what is it broken up into is really important, right? And it's even, kind of like this really old joke of how do you eat an elephant, one bite at a time. Well, breaking things up into ramp steps, the questions tend not to use delta functions, but they're there, and sine waves. But to look at a function and break it down, all right? Which, even though this is in the time domain, right? This shape here, right? If I put it in the frequency domain, is a Bode plot, right? And if you really look at it, it's just like a ramp in frequency. And of course, it's got to be scaled such that everything comes out on a log-log plot. And if you see some of my Desmos stuff, you'll see that's what I do, right? But taking a signal, breaking it up, recognizing it for what it is, right? Which then allows you to analyze it more easily, right? So then that gets into convolution, right? Which really, we have a system, time domain. We have inputs, we have the output, right? And in 98, right, we might have done something like this with a transient. The switch closes, and then we use our circuit analysis techniques to figure out what's going to happen. Where in 110, we more derived a transfer function, right? And then use mathematical processes to get our outputs for whatever input we are, right? But we can never really get away from the frequency domain, the time domain, because everything happens in the time domain, right? So even this, just as recall, this is a Bode plot really is a frequency response, right? But you would just put in different frequencies, measure the magnitude and the phase, and come up with that, right? So it would all happen here, where I would put in a sine, use convolution, right? And measure an output and get an attenuation factor and a phase factor. And I would just step this, right? I would make a table and go through that. So now the thing about convolution, though, is that in general we have things that aren't periodic. But this is where we first kind of learned about high and low pass filters and things like that, right? But by breaking up a shape into its component parts, you can rapidly do the convolution. Historically, convolution seems to be taught in the hardest way possible, right? Where the example in the book, which is a great book, has the input of a triangle wave, right, with a HT of a low pass filter. And they just go through every possible trick in this example, right, to get it done. But really, you have a ramp T minus a 2 ramp T minus some delay, right? You find the convolution of a ramp to an exponential, and then you just add and scale it all together, which comes at the end when you're doing the frequency domain, because it's very easy to show why that's so. But it all depends upon things being linear and time invariance, right? But as engineers, we know things are linear for certain conditions. They're time invariant for some certain amount of time. But that kind of breaking things up takes a very hard problem and, makes it reasonable. And then we have some classic HTs. 1 over RC e to the minus T. Okay. So some things that you just have to kind of have in your repertoire, right, is that's low pass and that's high pass, right? Now this is just more like what I'm about to tell you is just memorization, right? But the high pass has the delta function in it, right? Because it's detecting the edge. So if you need to memorize things, memorize that. If you see a delta function in there, right, at least for, let's say, problem 3, right, it's going to be, there's going to be a high, it's got to be a high pass. And if you think about it, right, you have, if I convolve a delta with the thing, I get the thing, right? So if I convolve a delta with a step, I get a step which has the edge, right? High pass are edge detectors, right? The Laplace transform of a step is 1 over s, which, right, s goes from, well, it's a complex number, it goes from 0 to everything, but really it can go from 0 to infinite frequency, right? So this passes this edge, you're passing infinite frequency, you're passing high frequencies, right? where here, right, and then of course, you're subtracting I'm just going to say low pass T, right? This is the low pass. So if I'm just going to stay over here, I get the original step, and then I'm convolving the step with a low pass, which rounds thing. This is the regular low pass, right? Oop, I want a better color. Sorry. Right, this is regular low pass. So minus low pass is this. Adding the step minus this gives us the edge, right? So you should probably do this yourself several times, right? Rather than just straight problems, right? Almost as if you were making your own cheat sheet. But you have to have this, in your head to be able to do the problems. Then the other part of question 3, you have 5 tau, right? And so if tau goes down, omega naught goes up. The smaller tau, the faster reaction time. So this is H of T low pass. This is the Bode plot of it. Okay, so this is time, frequency, omega naught. This is omega naught e to the minus t omega naught ut, and this is omega naught s plus omega naught. So when omega naught, when omega naught gets bigger, right, 5 tau gets smaller. Right, when omega naught gets smaller, 5 tau gets bigger. So here we have a form, and we're not even asking you to do, to find out whatever that is, right? But that's 0. You can tell that's a ramp. Yeah, it's probably a minus ramp flattens it out, but you just would recognize that this is DC, right? And DC in quotes because it's not that voltage the whole time. And then you have a step down. Well, the thing is I'm just going to kind of draw a crazy shape. All right. And just say that it's low pass. Right. And then there's my step convolved with low pass. Right. It's going to pass DC, and it'll take a certain amount of time to get there. Right. That's, no math, right? I'm integrating this area, and eventually the area, there's no more area to integrate because it goes back to 0, so this flattens. So over here, yeah, and a ramp, right? It's a slope. So if I do something like this, if that ramp goes up and I'm a low pass, yeah, there's going to be some delay and it's going to be tracking it. And then at some point, I'm going to have a DC, right? I'm just showing it a little bit below, right? Well, this is non-zero and it's passing. So it has to be low pass right from here. Now we have what this is just a negative step, right? And so it's going to do this, right? And again, it can go either back to 0 or a negative number, but it's, in this case, it looks negative. I'll just say 1, right? So it's passing a negative 1, and this negative edge is being rounded, averaged out, so that you just have to look at the DC parts and then how it handles the edge, and it's a low pass. And then how long does it take? So then, all right, so if this is DC and this is DC, and I want to do a high pass, where should the output go? Positive, negative, 0 in these regions. Where should it ultimately go? To 0, right? So it just depends on how long it's going to take to get there, right? So I'm just going to put this at 0, and then after some time, I'm going to put that at 0. All right, so now 0, it starts off at 0, all right? But here, it's actually detecting a slope, so it will pass that slope after some time, but it's taking the derivative. So it might do something like this. It takes a while to adjust, and then it's flat, right? Now it's DC, so it's going to take time to go back to 0. Now here is a negative edge, right? So I'm going to detect the negative part, right? And then it's going to go back to 0, right? And depending on tau, it'll either take longer or shorter, right? A longer, right? If it takes longer, if it takes longer, there's going to be some delay, and then it'll start to track. Oh, no, sorry. Then it'll start to flatten out, but then it goes back to Z, but it might take a very long time. And then this one will go like that, and it will kind of take longer. okay? So really, I'm just doing a kind of an intuitive or a graphical convolution of what's going on, all right? What do I expect? So that's kind of all in the time domain, right? Because that's where everything is measured, right? Then we got into transfer functions, right? This is the weirdest. Okay. We have our low pass and our high pass, right? And you have to be able to do Bodie plots. But you don't have to do complex Bodie plots, right? Prior, I could have it'll be second order. Okay. And there's a few choices. You can have omega naught equal omega 1. Bless you. Okay. Oh, and then there's a gain. Okay. And gain is usually 1, 10, and 100. And then for the high pass, it's, a similar denominator structure, right? So to be able to, use those asymptotes, right, to figure out what's going on is really important, because when we're doing system identification, right, and we have some kind of phase, right, the phase can be hard to find. So we can find omega naught with the asymptotic method, all right? The, the gain, the cutoff frequency, and that slope is really all you need to know. And the phase, right? Because the phase will tell you, like, is it inverting or non-inverting? All right. So we teach that first before filter design, so that you can, by creating Bodie plots, you'll be able to interpret Bodie plots to see if your filter's working. So if I say, oh, use the analog wizard, come up with a filter design. Okay, great. But is it really doing it by the time you're building it, right? So you have to be able to recognize, oh, that slope is 20, that slope is 40. There's 2 breakpoints. There's 1 breakpoint. There's peaking, all right? And I showed you a case study where I thought I was getting one thing, but I was actually getting another. Bless you. So the ability to create a Bodie plot is pretty important in the EE program, right? Just as in a skill it's itself, and as a subsequent skill, right? Now, yeah, then we have still more analysis, right? I can have an op amp, a two-stage op amp with some kind of Z network, right? Which would, it could give me a low pass with a gain or just a gain, plus or minus. And to be able to work that out and then come up with a Bodie plot, right? That's to be able to just find the transfer function. It's kind of like an EE98 skill, right? But a little more advanced. So it is like review. You have to be able to do that to get into 122. But op amps are short for mathematical operational amplifiers. And so when you're coming up with, I have a mathematical function I want to implement, you have to be able to break things up, right? So you're not designing, here's what it is, what does it do? Because when you design something, right, you say, well, I propose this circuit. I think this circuit is I think this circuit is a non-inverting amplifier. Okay. When you test it, you'll find out it's a Schmitt trigger because I swapped these two pins. So one, you have to be able to see what you did and what would happen, right? But then if it goes wrong, you have to know how to fix it. I'm going to put this one first. So now these are system diagrams, right? You have to be able to know how to derive a function from it. And then, yeah, you get given something and then what does it do, right? But this is, if you recall, this can be an op amp, right? But this can also be a control system where it's out of control and you have to fix it, right? And also when you have I don't want to draw, right? We know that that summer is an advanced summer, right? If I give you 1 over S, or more likely minus 1 over S, right? You know the circuit for that, right? So to be able to take an advanced summer, see this, what the feedback is, and come up with the system diagram, right? But this system diagram we use for the op amp for gain bandwidth, right? And we use it in control theory, right? So we've talked about different op amp models where that's just AV. And I'm just drawing these in different regions so they're not overlapping. So these are not the same open loop gain, right? That's the integrator style, right? I can even make it kind of double, right? Red would be AB omega naught, S plus omega naught. This would just be AV omega naught. All right. So our transfer function, right, has to be below this line. Right? And what differs from 98, 97 is the op amps were ideal, but now what was ideal? The open loop gain was infinite. Now our open loop gain is frequency dependent, but I usually give you a transfer function to do that, right? Those are the various transfer functions. And so the question is, what frequency does it stop working at? That's one. Or something's not working, what's the problem? And I can give you some plots, all right? But knowing about the frequency dependent of op amps is now, that like separates you now all from all the other majors. And not to, and what I find is that other majors, you know, and you can look back there, there's these posters of all robotics, and those are mechanical engineering faculty who are my friends, but they're all using electronics that we would teach, right? But they get into trouble when they don't understand the frequency limitations or the limitations of op amps. And so then they, you know, they call me up. You know, the best projects are multidisciplinary. I'm just saying, what I found is the frequency dependence of things is what separates us from other majors. Where like mechanical, right? Most of the lower division is the same. I see you, Jared. Most of the lower division is the same, but we don't know. We don't do heat transfer, right? Wait, can you speak slower? Yeah, I mean, if I had a magic wand, I'd make them on that way. But so Spartan Racing, seniors project, and it's certainly multidisciplinary. The rule is you gotta have at least two EEs on the team, otherwise things can go south. Or if they go south, it's harder to recover. The robotics club, I want to see them do senior projects, right? And that's multidisciplinary as well. Those are like the big ones you'll see on LinkedIn, right? But now, yeah, you just also need an EE advisor to advise. Sometimes, like when we would do the satellites, the aerospace people, they took care of it, and I just had to sign the paperwork because they were doing their thing, right? Um, but yeah, we are very flexible that way. Um, yeah, great question. So I already talked about the controls. I talked about this, and it's like kind of the same concepts again and again, right? So really, you know, what did we do after the midterm? I'm just showing a second order low pass, right? You know, high second order, low. And we had damping coefficients less than 1, equal to 1, greater than 1, under, critical, over, right? Or kind of under 1 pair complex roots, critical, heated roots, over 2 real roots. All right. I'm just showing the underdamp. But then, because it's second order, right? We can have band and we can have notch, which now I'm just kind of doing asymptotically, right? So you have to be able to identify these systems. Is it low, high, notch, band, and then an estimate of the damping coefficient, right? And then we had this thing of like, well, if this is 0 to omega naught, this is like infinite to, I should say 0 to infinity omega naught. That's like infinity to 0t. So 0 to infinity here, infinity to 0 in time, right? And we can figure out what's what. Now, that's great. But then we get into repeating functions. So if I'm giving you a period, I'm telling you it's repeating, right? And, you know, we're taking the Fourier expansion. So then we're going into frequency, similar to like a Bode plot, but we're talking about a signal, not a system. The signal has to repeat. Unlike a Bode plot, we can go at 0, right? So we have some kind of DC, and then we have harmonics, right? So sharp edges, right, are sharp, I should say, discontinuities cause infinite harmonics. That's still not quite right, is that, although it's true, right, that's discontinuous, right? But really, if you have, right, this is discontinuous there. So that'll have infinite harmonics. The only thing that doesn't have infinite harmonics is like the sum of sine waves and cosines that have a finite sum, or you're multiplying a finite number of sines and cosines together, right? So sine squared omega t, right, really looks like this, right? And it has a DC offset, and you can see it's smooth, if you will. But absolute value sine has this discontinuity. But I can easily determine, you know, I can have a square wave, all right? And it's on 1/2 of the time. That means at 0 hertz, it's there, right? I get 1/2. But let's say I'm going minus 0.5 to 0.5 and it's 50%. Well, the average is going to be 0. So it'll be 0. So I could have a sine wave like this, a square wave like that. So let's say 0 to 1, minus 0.5 to 0.5, right? They will all have, this one has no DC, but then we'll have the classic, harmonic type pattern. Right. And that'll have the same classic pattern. So you can really figure out what's going on just by finding, and then, yeah, what if I had one square wave like that, and then one square wave twice the period, right? Well, the fundamental frequency would be, right? So you can do the first two terms of a Fourier expansion pretty much in your head, right? Which is required for 60. Now, how is it all tied together? Well, I have a microcontroller. You might not know, but pins are limited on a microcontroller. Digital to analog converters on a chip take area, right? So what you can do is have a pulse width modulated signal, right? That's going to give me a half, right? It's going to give me like a quarter. And that's going to give me 3/4. So the DC part of this, the average of it is 1/2. The DC average of this is 1/4. The DC average of this, higher, 3/4. 0 frequency, frequency. Okay. Now, The 50% duty cycle has the largest error, the largest ripple, because that its first harmonic is the largest. So it's actually bigger than 1/2. Now at a quarter, I'm not showing the infinite, right? But it's around the same or less. And then 3/4, well, 3/4 is at least higher. So the thing is all these levels will have ripples because I can't perfectly get rid of that, right? An ideal filter would be a box. I give the DC and this goes to 0. Get the DC, that goes to 0. DC, that goes to 0. But that doesn't exist. There's always some signal there, and there's an infinite number of frequencies, so you will see some kind of ripple, and you're trying to get rid of that with a filter, right? So the trick is, because we can do the Fourier expansion, I can get the DC part, right? I can understand it. Then I can see that the harmonics, the first harmonic for the half will give you the worst ripple. What that means is you only have to test the one. With normal digital to analog converters, you have to check every code, right? So if I had a 4-bit digital signal, right? 4-bit digital to analog converter, I have to check this, and then I get 0. Then I have to check this, and then I get the least significant bit. Then I have to check this, which would be 2 least significant bits, 3, so on. So if 16, you got to check all those states, right? Here, I only have to check one, and because the rest of the areas will be less, all right? And what kind of filter does that? A low pass, right? What is the best kind of filter? Most, Butterworth, right? That means the damping coefficient is 0.707. Complex poles. Right? So I get my minus 40 dB per roll off. There is no peaking in the Bode plot, but in the step response there is. All right. So by designing a pulse width modulated DAC, right, you're getting the Fourier, you're getting the filter design, and you're kind of tying the whole course together. But yeah, I mean, the learning objectives of the course is, yeah, to actually make a decision between EE 132 to study more controls or to study communications 160, right? Although for this year, that's not going to be possible, right? Then you have 122 where you find out more non-idealities of the op amp, and you do more advanced op amp designs, which then you go into 124, and you're actually starting to design the inside of the op amp at that point, right? But if you know that you're trying to get rid of noise, you're trying to average it out, low pass filter, you're trying to detect an edge, high pass filter, you're trying to keep a frequency and get rid of everything else, band, trying to reject something, notch, right? That's pretty good. And to be able to identify everything. So that's the exam and how it ties together. Not every problem ties with everything, because otherwise I could ask one problem, right? The exams are 2 hours now, by the way, just so you know. Are there any questions? on, now it could be like whatever, right?
50% of the learning here.
Yeah.
Is that only trying to make a DC signal? Like if you're trying to make a sine wave with some frequency, could one of the other, because you're just doing digital one, right? So if you're doing a frequency of the input square wave, if you want to make that sine wave frequency, wouldn't that have the lowest?
Well, the 50% for a square wave, that fundamental frequency is going to be the lowest thing, right? So now, I guess the question is, I have a DC, right, which is going to go up and down, and then I have my fundamental harmonic up and down. And so you might think, so now I want to keep this sine wave, right? And the way I've drawn it is that it's like it's not even touching. So let me try to maybe draw it a little flatter. And yeah, so there's a couple of things, right? That's F naught. For 50%, the next one is 3 F naught. But for the other ones, you actually have 2 F naught. So you have something closer, right? So what it is, what do I remember? I remember the 50% one, and I remember that it's, the way it works is that only the odd frequencies have any energy in them. So if I were to use greater than a half or less than a half, right, I would have this harmonic here. Now, it's probably bigger than that harmonic, right? But that's something that is less attenuated than this, right? And then, yeah, the more DC, right, the more it'll raise the signal level, right? But how I would, so if I said, off the top of your head, which one do you think would be best? It's looking like 50% would be best, right? But what I would probably concentrate on is once I did that, what order of filter do I need to zoom in on the one that I want, right? Also, I could probably, all right, well, no, I'm not going to go down that path. But that's, and then it's just like what tolerance you can have. But yeah, I'm thinking the other ones have higher frequencies, but then when you sum them up, it can be a little counterintuitive of the harmonics. So I'd probably have to actually go and do the derivation. The 50% one, there's a derivation in the notes and it's summing up the energies, right? So I would have to sum up the energies. The problem with summing these harmonics is that, not only do you have, not only for the non 50%, you have B's, you have the sine waves, you also have the cosine. And so then you have these phases that you have to sum up, and can be pretty involved mathematically. But that's why they go for, they're trying to sum up the energy. Because if you're trying to sum up these harmonics with their various phase and things like that, it'll be difficult. I would have to do it. Okay, that's a great question. Anything else? I know it can be embarrassing to raise your hand, but like I've given my set talks, right? And I think they're wonderful, but you might not get it. So I don't know what you don't get. I'd like to know now rather than on the grading the exam. So if you could just, this is our time. Sure. What is it? Yeah.
Roger Dan, one pass.
Is it a my open math?
But you use the formulas that'll happen like 7 over.
Uh, I measured it. And I think I don't think, here's the thing. I don't know these equations off the top of my head, right? But if I have a low pass filter, right? Right. There's a rise time and then like a settle time, right? But these equations are out there, but they're only for complex, or I should say, underdamped systems, right? Where you just look at the plot and like that's the rise time, and there's an equation for that. And you look at the peak, and so when you get to below a certain level of oscillation, there's an equation for that. What I had been looking for is what about critically damped, right? I was looking for a 5 tau, right? So what is we have 1 minus e to the minus time is 5 tau, right? And that's tau. And that gives me a number, how close it is to 1, right? So then I just kept picking times until I got to that closeness. And what I found is for a critically damped system, which you had to know it was critically damped, you get 7 tau, right? The problem though with the overdamped is you have two different rates going on here. And now if one is much, much bigger than the other, it's practically a first order. You can get away with it. But I could not come up with a question where you could look at it and you could just tell me. Now I have these old notes. I thought I removed them where I went through, I would make an assumption and then try to backfit things and find out what it is. Honest to God, just take the Bodie plot and you might say, well, and then find the system from there. But that might not be, you might not be able to do that. So it's a trick, right? But I mean, it's a real thing, don't get me wrong. So if I have the step response, right, and I convolve that, right, um, I get H step, right? But if I do this, okay, if I take the FFT of, I have to have a square wave, right? Of the derivative of the FFT, and then I take the FFT of the system, right? So if I'm doing, that could be my square wave, and this could be my output. And again, now this is repeating, right? So if I take the derivative of this and the derivative of that, and then take the FFT of that, FFT of the derivative of the out divided by the FFT of the derivative of the in, you get a Bode plot. The reason why I do the derivative, it can be very hard to get an impulse response, right, to set that up properly. But you can do a step response. And the derivative of the step is the impulse response. I mean, the derivative of a step is the impulse. The derivative of the step response is the impulse response. And then because it's repeating, you can just take the FFT, take the two ratios, and you will get it, right? It's buried in there somewhere, right? I just found that it wasn't, it was too much. That's why I don't use it, but you can also put in random signals and watch it over time, and the Bode plot will emerge as well, right? It doesn't have to be one sine wave after the other, right? Because a random signal over time will have all the frequencies in it. You just have to wait. Okay. But the delta function, right, when you take the Laplace transform of that, does have all the frequencies. The Laplace of a delta is 1. So it's all there, right?
You know what room number we're in?
Hmm?
Do you know what room number we're in
Oh, we got to be here.
for the final?
Yeah, yeah.
Oh, it's this one.
Yeah, no, hold on a second. The way you're asking that is making me think others aren't doing that. Who's not doing that? Oh,
Yeah,
well,
3:37.
okay. So for final exams, you can change the day and time with permission. Okay. So, so there's two sections of 112. He wants a common final. So he could push it to a Saturday as long as he gets permission and tells you like at the beginning of the semester. And 118 is what? 180 people in there, right? That's difficult. I mean, we can do 80, but yeah, he can then ask to split it up. But they're all following the rules. Hey guys, let's have the final exam today and I'm done with you, that's illegal. You're supposed to have a,
Right.
what? He said that's illegal, or
You set the activities right there.
Maddie 153? What did he say?
He likes to play a little faster
Yeah, just the.
until someone tells him to first.
Well, no, he got in trouble. Yeah. Oh. Listen, this guy, no, I haven't, there's nothing to be ashamed about, is that there's rules about culminating experiences, right? And you're supposed to have a culminating experience, right? Whether it's a dance project, even I was talking to somebody where they had to do jujitsu and somebody was trying to have it on the last day. And no, I report that. And so, yeah, some people tried to change midterms like it's a final. You cannot do that. If you, at San Jose State, when we say that the midterm is gonna be a certain day, it's got to be that day, right? Because, students who have a lot going on in their lives need us to be organized so that you can be organized. So if I say the exam is on, March 10th, and then I start swapping it around, like if, I mean, people might have to switch their daycare, their job, all this business, right? No, it's really serious. And the final exam thing is ultra serious. We have to get permission to change it before the semester starts. It goes in the green sheet, right? Now, yeah, if something were to happen, right? We could figure some, like I've had people, they have changed the midterm, and what they ended up having to do is they had to give it twice. They had to give it when they said, and then they had to give it when they changed it. And then nobody complained. All right, there's no, like the exam thing is for real. You can't be playing fast and loose. You let me know. And, because and I can tell you the other side of it. All right. There's somebody attending my alma mater, right? UConn, and exams are kind of done by consent. Well, should we have it next week? No, not next week. We'll have it later. And it's chaos. It's absolute chaos. Now, life is chaotic. And if I put in my learning objectives, the successful student will learn how to deal with chaos. Well, then, okay, I could probably add some chaos. But there's already chaos in our lives. I don't need to add it, right? So, yeah, those syllabi are supposed to be contracts, right? But like if a mistake is made, you can recover, right? It'll say the schedule is tentative, maybe the topics, but no, you better have things when you say you're gonna have them. That's a fact.
So you have your syllabus, you have the dates for like.
Right,
if you're
right.
Right, and last week you said he wasn't out, it says held pending. Or.
Maddie 153, right?
Waiting for number.
Right, but that's coordinated by somebody. All right, I'll check into that. All right. Yeah, Joe?
One time you were disappointed people weren't remembering stuff in your senior project. What was
That's very close to what I'm saying. No, I changed 110, not because students weren't remembering 110 in senior project. There were skills that they never used. So I'm like, if this isn't used, and I can't like, and it was something people liked, is that you could have a mass, a spring, and a damper, and you could turn that into an RLC circuit and analyze it. People loved it, but I know 132, it's not used there, it's not used in 122, and nobody used it in senior project. I'm like, let's concentrate on controls and things like that. But no, it wasn't a deficit of the student. I felt it was a, it was an effort to make 110 more exciting, to add that thing there. But then, now, yeah, you probably know what I am disappointed in, and, certain people not holding a standard in 98. You've probably seen my emails on that. But, no, that's really what it was. It just, if you're not using it, why test it? Why, you know? Although it was pretty neat. So anyway, listen, guys, it's really been a pleasure. All right. I know I have like harangued you and harassed you for coming to class and all that, but really, that pretty much stopped on midterm 2 when everybody pretty much did well, right? It's, it might not seem like it, but man, it's done with love, all right? Um, and yeah, if you know me, you can't say the word without hard in it somewhere. Okay. So, or no, tough. The word tough. Yeah, all right. But just get a good amount of rest. Do whatever problems you do well, right? And I'll leave it at that. All right. See you soon.